Okay, let's dive right into this explainer. Today, we're pulling directly from Chapter 17 of our source material, and we're looking at a genuinely fascinating concept: how to use ontologies as a shared language. The goal here? To finally align our human teams, and absolutely crucial for today's world, safely integrate AI into live production environments. I mean, if you've ever felt like your engineers and business operators are speaking completely different languages when a system breaks, or if you're pulling your hair out trying to figure out how to put hard guardrails around unpredictable AI agents, well, you're in the right place. Let's get into it.
So picture this. Imagine it's 2 a.m. on a Saturday. Your pager is just barking at you. You drag yourself out of bed, you crack open your laptop, and you're staring at two completely contradictory dashboards. Your infrastructure dashboard happily reports 99.9% uptime, latency's looking great, under 200 milliseconds, and you've got a beautiful sea of successful HTTP 200 statuses. According to the platform metrics, the system is absolutely perfect. But the pager is still going off, the business logic is failing, customers are furious, and you're stuck staring at a terrifying, silent failure, where the metrics are basically lying to you, telling you everything is totally fine.
And you know, this perfectly illustrates the real root of the problem. It's a silent failure caused by a complete breakdown in communication. In complex systems, data is absolutely everywhere, but actual truth? Truth is incredibly scarce. You might have developers, operations folks, and business teams all staring at the exact same system, but they're using totally different definitions for what availability actually means, right? To a developer, it just means the server's running. To a site reliability engineer, it means network latency is low. But to the business stakeholder, it means the customer's utility bill is mathematically accurate. When these teams don't have a unified domain language, absolute chaos ensues during an incident.
Okay, Section 1, the solution, building a shared language. So how do we fix this chaos and put an end to those silent 2 a.m. failures? We have to establish a shared translation layer across the entire organization. We need to stop relying on vague vibes and fragmented definitions.
Now we do this using an ontology. And look, I know ontology sounds like a dense academic concept or a theoretical knowledge graph collecting dust on some company wiki. But in the context of modern observability, it's actually a highly practical operational map. It maps out your system's core objects, their relationships, and the rules governing them. It's essentially how organizations govern their complex socio-technical systems, ensuring that critical terms like uptime, user, or incident mean the exact same thing to every single person and, crucially, every single machine interacting with that system.
So we take that theoretical map and implement it using semantic conventions. You can think of these as the ultimate translation layer for your organization. For the business side, they provide a really clear vocabulary that maps directly to customer value, things like costs or usage. For your engineers, they ground those abstract technical metrics into actual real-world business processes. And for the system itself, these semantic conventions act as rigid schemas that turn ambiguous, messy data into verifiable truths. For example, if you standardize the exact name of a variable, let's say user_account ID, across every single codebase, there is literally never a debate about what data you're looking at during an outage. It's a real game changer.
Moving on to Section 2, the blueprint, mapping the domain. Let's ground this with a concrete case study of an energy management system, just to see how we'd actually build this out in practice.
Okay, so this system's main job is to ingest raw energy usage data, price a utility bill, and then use an AI agent to suggest ways for the user to save money. To make this reliable, we have to define our core entities, basically the nouns of our system. First up, we have the interval series, which is our input. It's a time-stamped series of raw usage data. Then the tariff, which is our logic, a deterministic rule set for pricing. Next is the bill set, our calculated output. And finally, and this is where things get really interesting, the action plan. This is our AI's proposal. It bridges the massive gap between a human request and specific, actionable system operations.
When we build an entity relationship graph, what we're doing is visually connecting our objects to show the underlying semantic grammar of the whole domain. The interval series quantifies the bill set, and the tariff prices it. But notice how the action plan sits entirely outside that deterministic flow. It doesn't actually produce a bill directly. Instead, it just proposes tentative changes based on what the homeowner wants, and it waits patiently to be tested against the fundamental physics of the rest of the graph.
Now, once we have our nouns mapped out, we absolutely must define invariants. These are your unbreakable mathematical truths. For instance, coverage. This invariant dictates that every single timestamp must map to exactly one pricing window. No gaps, no overlaps, period. Another is arithmetic. meaning the total cost of the bill set has to perfectly equal the sum of the individual intervals. This is critical, you guys, because AI models, they can easily write bad code, but they cannot break a hard-coded mathematical invariant. If an invariant is violated, we know instantly that the system is broken, even if standard code exceptions aren't throwing any errors.
So, we glue all this together in our code using something called metadata provenance. Actually, think of it more like a strict chain of custody for your data. By establishing these semantic conventions, we make sure every single data point has a crystal clear lineage. So when you look at a bill set, you aren't just seeing a dollar amount. You see exactly which specific input_series ID and which applied tariff ID produced it. You can logically reason about exactly how and why a piece of data exists, well before you ever allow an AI agent to start altering things.
All right, on to Section 3. Taming non-deterministic AI. Because introducing AI agents into this perfectly mapped ecosystem, it creates a massive complication. AI brings non-determinism into the mix as a core feature, which is tricky.
We have to contrast our predictable, deterministic math engines against these dynamic, probabilistic AI workflows. A deterministic tariff engine runs on hard, unyielding logic. It's predictable. But an AI agent, it operates on fluid, vague, natural language. Think about a user just typing in, "Hey, make my bill cheaper next month." I mean, that is incredibly vague. The AI has to interpret that human intent, which makes its outputs inherently unpredictable and, frankly, risky. And this right here is exactly why that action plan entity we talked about is so absolutely critical. The action plan serves as the bridge between that fluid, unpredictable AI intent and our rigid system rules. But here is the major takeaway, so pay attention to this. It acts as a proposal that remains totally and completely untrusted. It is a tentative object that we do not execute, period, full stop, until we have thoroughly validated it against the unbreakable mathematical laws of our system. This leads us perfectly into Section 4, the AI sandwich architecture. Because to safely execute these untrusted action plans, we need a really rigorous continuous integration or CI pipeline. We definitely can't just rely on manual testing or crossing our fingers and hoping for the best.
We have to evaluate the AI's behavior before it ever gets near production, and we do this through 3 highly structured steps. First up is the deterministic layer, where we assert the math holds up, making sure there's no broken arithmetic. Second is the simulation layer. Here we feed the AI's proposed changes into a physics engine that runs a shadow version of our system. So if the AI hallucinates that a plan is going to save a user $20, the simulation actually has to execute and confirm that exact dollar delta in a safe, isolated sandbox. And third, the semantic layer, where we evaluate the quality of the AI's communication. Now, in that semantic layer, we use golden dialogues. These are predefined ideal interactions to score how the AI communicates. And we can enforce a strict automated gate here. For example, we can put a hard rule in place that rejects any AI proposal if the model's internal confidence score drops below 0.6. This is huge because it prevents a hesitant or hallucinating model from ever progressing. It provides an immediate, automated block against poor AI performance well before a customer ever sees it.
And this whole setup is what we call the AI sandwich architecture. It's such a great visual. We take our dynamic, unpredictable AI workflow and we literally wrap it safely inside robust deterministic guardrails. So the proposed action plan gets sent to a simulator, and only if it passes those rigorous invariant checks, like perfect time coverage and flawless arithmetic, does it actually become a safe executed action. Our ontology definitions act as the critical interface here, keeping the entire system totally secure from AI unpredictability. Finally, Section 5, the Observability Data Flywheel. Let's explore how we take this beautifully structured ontology and apply it directly to continuous deployment and live production. This is how we create a system that actually improves itself. The ultimate payoff of all this work is achieving true signal parity. Signal parity simply means that the exact same language and structure you use to test code in your CI pipeline is the exact same language you use to monitor it in the real-world production environment. The logical assertion that stops a bad pull request from merging is the exact same query that triggers an incident in production. This completely closes a massive operational gap because suddenly your testing and your monitoring are speaking the exact same dialect. Having this shared instrumentation creates this incredibly powerful data flywheel. So let's say your AI model fails to understand a weird edge case in production, maybe something like a rare leap year tariff change. You capture that exact artifact directly from the trace, you add it to your evaluation suite, and you automatically block any future deployments until the model can pass that specific scenario. Treating an AI failure exactly like you treat a traditional server latency spike fundamentally changes how teams manage AI reliability. It's brilliant.
So by adopting ontologies and semantic conventions as your shared language, you're transforming unknown unknowns into clear, actionable signals. Dashboards stop disagreeing, and teams finally share the exact same reality. So I want to leave you with a question to really think about. The next time your pager fires at 2 a.m., is it going to be a confusing, panicked hunt for disjointed data? Or will it be a directed, calm search where your entire team is completely aligned? Thank you so much for joining me for this explainer today. Start mapping your domain, stop trusting the vibes, and really take control of your systems.